but it would be greatly suppressed. Yeah. So here's kind of a structure property relationship to some degree. That is, as the material goes to these nanocrystals, then you've created this opportunity for charging this, and this becomes your flash memory, which is hopefully recording the video of this review session on that SD card, right? And so hopefully it's storing that. Here's also non-volatile memory. And you remember those trench capacitors I showed you? That's the DRAM, right? DRAM. So then here is an edge dislocation. So this is really a misfit dislocation. So that's maybe one lattice constant on top of another lattice constant. And here, this was just to stretch the bonds from this to this or this to this was just too much. And basically the covalent bonds said, no, we're not going to go there. They're like elastic bands, right? They only stretch so far, and then they break. So this guy really couldn't satisfy. And so then these guys hooked up with the nearest neighbors here, and this guy's left unsatisfied. And so recognize there are dangling bonds going into the board. That whole row of atoms has a fourth covalent bond that's unsatisfied. So that covalent bond is sitting there unsatisfied, and it's wagging its tail or its ears, and it's looking for something coming by. So an impurity or something like that. So it's gonna scatter electrons. It's not a good thing usually. So you can have edge dislocations, screw dislocations. You can have all these dislocations, and you're not a material scientist. But if you are interested in this field, there are some technical electives you can take in material science. You actually learn to do transmission electron microscopy. I think it's a 2-course sequence. You take one course that's more lecture-based, so you learn the theory, and then you actually go to the lab and you actually do electron microscopy. So some of my graduate students do that as sort of their minor. So here this is looking at the grain boundaries. Again, I'm not sure I would classify this as structure property, but they're looking at the structure, and here they did a stain etch, and they're just using a microscope. But you don't really know necessarily the property. Has it changed probably the mobility has changed. I mean, I would surmise that the mobility of this would be superior to the mobility of this, because, is this the same magnification? It's two different materials. Okay, so it's apples and oranges, so I don't know. But if this was the same material, then I would surmise this is a higher mobility, because it's more crystalline, the grain sizes are bigger. Okay, so the misfit dislocation is, recognize we want to put anything on anything for maximum flexibility. So let's say we want to do blue-green LEDs or lasers. You're putting gallium nitride on sapphire, and so you have the misfit dislocations. And so this doesn't show where aluminum oxide is, but it's quite a large lattice mismatch. Let's maybe look at. There's another take-home problem I might have you do at some point. I don't know. I'll see how you guys handle the double diffusion. But there could be where you actually design a laser or an LED for a certain color, and you have to determine the quantum well size. You have to determine what material system you're going to use, and you have to determine what substrate you're going to put that on, and then you have to determine what the size of the layers, the thickness of the layers are that are epitaxially grown, and based on the quantum mechanics, the confinement in a finite well, you determine which wavelength that is going to determine. So you could be mixing and matching these different tie lines. But normally, we would do the classic is gallium arsenide, aluminum arsenide, and you can see how there's no strain. they're right on top of each other. So that really is beneficial. So the lattice constant of gallium arsenide and aluminum arsenide, there's no strain, no misfit dislocations there. But if I want to put indium and tinamide on indium arsenide substrate, then good luck, brother, because I'm going to get a lot of misfit dislocations. So I'm going to be limited by how much antimony I can put in before it breaks down. So this is really it. This is your Jenga towers. This is the homoepitaxy of one crystal of the on top of another, where they're the same lattice constant. So it's a homoepitaxy. And here's a heteroepitaxy. So this particular case is a larger lattice constant on a smaller, and see it. There's a deformation. It strains. It tries to accommodate, but at some point the Jenga tower pops, and you get a row of atoms every so often, right? And so that means that this was the lattice constant was too different, and the thickness got to be too large. You know, it might have accommodated that strain if it was 1 to 2 monolayers thick, but once it got to be 3, then it was the strain energy was too much. So it became, the terminology I like is that it became, where is it in here? It became energetically favorable to produce a misfit dislocation to release the strain energy. That's my preferred terminology, but you can use your own words. And so here's the critical thicknesses of different materials. So this should make sense, because as you go to pure silicon on silicon, the critical thickness goes to infinity, because you're just putting silicon on silicon. And there's no limit to that. This is showing how I can look at this. This is more information than you need. Shows me that I can inspect this at the atomic level. And remember, this is something that actually showed you that misfit dislocation generation is not fiction. This is actually something I observed in first principles in the reactor during the growth. And you see the lattice constant change. So, yeah. So the strain, here's what the misfit dislocations look like from the side. This is what they look like from the top. Okay. Ways to make bulk epitaxy. So this isn't a process class, but you should kind of know where things come from, I think. And so here's the Tucholsky, and that led to the ability to make those boules and those large ingots or crystals. And so here's the Tucholsky method, and then you slice that, make the wafers, and here you can see the process in that video. Also helps, hopefully. And so you make the whole thing, and different ways. You don't have to know all these, given this isn't a process class. And then, but do know that, you know, I can modify. I can do implantation or diffusion, right? So here's diffusion, and here's implantation. What's the consequence of the diffusion? I mean, this is kind of a finer level, not really necessary for the 30-30, but you can see how the diffusion, it diffuses down and laterally. So this is less controllable. It's kind of messy, right? It's going all different directions, meaning isotropic. The implantation is more directional, but of course we get all that damage. So, but I can very precisely deliver through this railgun, you know, this ion implanter, I can precisely deliver atoms, either deep or shallow, whether they're heavy or light, you know, so we can figure that out. Okay. So we can concatenate different implantations, get different profiles. This is going to come up when we get to transistors. We will come back to the implantation. So some of the older generation transistors, we could set the threshold voltage very precisely by being able to implant right at that famous SiO2 silicon interface that we were talking about earlier. So by being able to put that right there, that'll become very, very important. So there's ways to make devices through epitaxy. And so that could be liquid phase epitaxy here. Who's trying grow the crystals at home? How many takers do I have? 1, 2. That's it? 3? Okay. Sure. So here's the VPE and MOCVD, MBE, all these epitaxies. Right? So then that's that. The next slide deck is probably much, much faster because this is more the